Chapter 7, Navigating with Infrared Headlights. The Bobot can already use whiskers to get around objects it detects when it bumps into them. But wouldn't it be better if the Bobot could just see objects and then decide what to do about them? Well, that's exactly what the Bobot can do with infrared headlights and eyes like the ones in Figure 7.1. The infrared headlight is an infrared LED inside the light shield that directs the light forward just like a flashlight. The infrared eye is the infrared receiver that sends the basic stamp high or low signals to indicate whether it detects the infrared LED's light reflected off of an object. So you can see here in Figure 7.1 how it shows an object is detected. The rays coming out of the infrared LED are drawn with this arrow here. And if it bounces off an object, the arrow coming back is infrared light coming into the infrared receiver here. And on the right side, we see that there's nothing to bounce off of, so the infrared LED light just keeps going. It doesn't bounce back, so the infrared receiver doesn't see anything. Okay, infrared light. Infrared is abbreviated IR, and you can think about it as a form of light the human eye cannot detect. For a refresher, take a look at 6.2 on page 171. Devices like IR LED introduced in this chapter emit infrared light, and devices like the phototransistor from the previous chapter and the infrared receiver from this chapter detect infrared light. Figure 7.2 shows how the infrared LED and the Bobot uses as a tiny flashlight is actually the same as the one you can buy out of any TV remote. The TV remote sends IR messages to your TV, and the microcontroller in your TV picks up those messages with an infrared receiver, just like the one in your Bobot, which it'll use to detect IR reflected off of objects. Okay, so here's that picture. We have our infrared LED here. It's inside remote controls. They modulate that as they send it to a TV, and the TV has a infrared receiver in it that demodulates it and gets the messages off. Note that the TV remote sends messages describing which button you press by rapidly flashing the IR LED on and off at a rate of 38,000 times per second. That's around 38k hertz. The IR receiver only responds to infrared if it's flashing on and off at this rate. This prevents infrared sources like the sun and incandescent lights from being misinterpreted as basic messages from the remote. So to send signals the IR receiver can detect, your basic stamp will have to send signals in the 38,000 hertz, or the 38,000 range too. The PBasic language makes short work of that task with just one line of code to transmit the signal and a second line to check the IR receiver. And there's a note here, some fluorescent lights do generate signals that can be detected by the IR receivers. These lights can cause problems for your Bobot's infrared headlights. One of the things you will do in this chapter is to develop an infrared interference sniffer that you will use to test fluorescent lights near your Bobot courses. The light color sensors inside most digital cameras, including cell phones and webcams, can all detect infrared light, which gives us a way to see it even when the eye cannot detect it. Figure 7.3 shows an example with a digital camera and a TV remote. When you press down and hold the button on the remote and point its IR LED into the digital camera's lens, it displays the infrared LED as a flashing bright white light. Okay, so when we look at it just by holding something on the remote so that it sends, and we point it into our eye, we don't see anything because we don't see infrared light. But digital cameras can detect it, and what happens is it shows up as a white light. Okay, the pixel sensors inside the digital camera detect red, green, blue lights And the processor adds up all those to determine each pixel's color and brightness. Regardless of whether a pixel sensor detects red, green, or blue, it detects infrared. Since all three color sensors detect infrared, the digital camera displays all mixes of the colors together, which results in white. Infra means below, so infrared means below red. The name refers to the fact that the frequency of infrared light waves is less than the frequency of red light waves. IR wavelengths and their uses. The wavelength our IR LED transmits is 980 nanometers, and that's the same wavelength our IR receiver detects. The wavelength is in the near infrared range, and the far infrared range is 2,000 to 10,000 nanometers. And certain wavelengths in this range are used for night vision goggles and IR temperature sensing. Okay, so activity 1, building and testing the IR object detectors. In this activity, you will build and test infrared object detectors for the Bobot robot. Gather the parts enlisting Figure 7.4 to help identify the infrared receivers, LEDs, and shield assembly parts. Okay, so the IR receivers, we'll have two of them. They look like this. They're pretty easy to find. The infrared LED, it looks a little bit different. You need to be careful that you get the infrared LED and not the photo transistor. So the infrared LED, I believe it's going to be clear. And we'll look for the two things that'll look clear like an LED and not colored are going to be the infrared LED and the photo transistor. So the photo transistor is a little more rounded, or a little flatter on the top, and the infrared is a little bit more bulbous or more rounded dome. So we just got to make sure we get that right. And let's see, there'll be a couple 220 ohm resistors, a couple 1K. We used those for the whisker project, so it should be the same as the whiskers. So we should just probably be able to leave those exactly in place, most likely. So you want to be aware of that when you disable your whiskers. And then we'll need these two shield assemblies. Okay, building the infrared headlights. Insert the infrared LED into the LED standoff. The larger of the two shield assembly pieces is shown in 7.6. Make sure that the infrared LED snaps into the LED standoff. Slip the LED shield, the smaller half of the LED shield assembly, over the IR LED's clear plastic case. The ring on one end of the LED shield should fit right into the LED standoff. Use a small piece of clear tape to make sure that the two halves of the shield assembly don't separate during use. Okay, so we should have some tape for this. Alright, and so here's what we were just talking about. Basically, you push that the infrared LED down into the case until it snaps, and then put this top part on, and we can cover it with a little clear tape to keep it all assembled. Okay, IR object detection circuit. Figure 7.7 shows the IR object detection circuit schematic, and Figure 7.8 shows the wiring diagram of the circuit. In the wiring diagram, one IR object detector, IR LED, and receiver is mounted on each corner of the breadboard closest to the very front of the Bobot. Okay, so disconnect the power from the board and servos. Build the circuit in 7.7 schematic using Figure 7.8 wiring diagram as a reference for parts placements. Okay, so our schematic shows here pin 9 in pin 8, and pin 2 and pin 0. Now, I'm hoping that pin 9 and pin 0 were the same as the whiskers, but they might not be. But if not, we'll just move those 220 ohms from 220 ohm resistors. I think they're brown, black or something like that, to to pin 9 and pin 0 from the whiskers. And then we have our emitters, our LEDs, infrared LEDs, on port 8 and port 2, and those will have 1K ohm resistors going to the LEDs. So it should be pretty simple. Okay, side by side, the new board's on the left, the old board's on the right here. So basically we're putting the LEDs up here on the front in really about IO the port for the breadboard, like port 2 and 4 here, and the second and fourth to the last there, and then the detector will go right behind it. And let's see, it looks like the emitter on the detector will be connected to the 1K resistor in here and going into port 0. And then the second one will be ground. We'll jumper that up, common ground. So the middle leads on the transistor are ground, so we'll ground those all together. And then the far left lead will be the power. So this one, they designate the power with red. It'll be jumpered with the right pin on the other receiver. And then that will be jumpered into VDD for the power. And so remember, this is a 3-pin transistor. So when light comes in, we'll get the power coming from VDD flowing through, because the base is set up by the infrared light coming in, and that will send power to our I/O port. So we'll see a 1 if there's light coming in to our infrared receivers. And it's the same thing on the other board pretty much here. Same exact wiring, it's just that there's the extra servo stuff that's kind of in the way. Alright, so object detection test code. Your Robot's infrared receivers are designed to detect infrared light with a 980 nanometer wavelength that's either flashing on and off or varying in brightness at a rate of 38,000 times per second. The infrared LED emits a 980 nanometer infrared, so that's taken care of. All we need to do is make the LED's brightness vary brighter and then dimmer at a rate of about 38K. We can do this with the same command that we've used to make the Bobot speaker play a tone at the beginning of each program. It's called frequency out, or freak out command. Okay, it takes 2 lines of code to test the presence and absence of an object using the IR object detection circuit. Here's an example that tests to find out if an object is in front of the Bobot's robot left IR detection circuit. So we send a freak out to pin 8, and it's going to be, there's 38,500, so that's the 38K hertz. And then we do an in9 to see if there's anything reflected coming back in after we send this out. So the command freakout 813038,500 makes the IR's LED brightness vary, getting brighter and dimmer at 38,500 times per second. It does this for 1 millisecond. All right, so that 1 is the hold time. So this is the frequency, the hold time, and then the pin is the first argument. So pin 8, hold it for 1 millisecond and do 38,500. All right, IR detect left equals in9 stores the IR receiver's output in a variable. The detector's output will be high if it does not detect 38,500 kilohertz reflected off of an object, or low if it does. So the value in9 that gets copied to IR detect left variable will be 1 if no object is detected, or 0 if an object is detected. All right, always use IR detect left equals in9 right after the freakout command. The basic stamp only has a brief time window to copy the binary signal it gets from the IR receiver to the variable. The IR receiver sends a low signal while it detects 38,500 kilohertz IR reflected off of an object, because in 9 to store 0, which causes in 9 to store 0. When the basic stamp finishes transmitting freakout signal and moves on to the next command, it stops sending the signal. So the program has to use the in9 to catch that 0 value before the IR receiver realizes the 38,000 signal stopped. It only takes a fraction of a millisecond for IR receiver to realize that signal is stopped. And after that, the output rebounds to a high, and in9 stores 1 again. All right, so the idea is that if you do something like print or call some other subroutine or do any type of other operations, you might have missed the signal bounce. Okay, so here's the example. It's really simple. We just declare a variable up here called IR detect left. It's a variable of only size 1 bit, so it's only going to hold a 0 or 1. We have a loop, a do loop, so it's going to go and do this forever. And what it's going to do is it's going to send that 38 kHz signal for 1 millisecond, and then it's going to detect it, and then it will just print out whether it did or not as a binary, so it'll print out a 0 or a 1, and then it will wait for 1/10 of a second. So it'll just do that forever. So it'll have a 1/10 of a second pause, 100 millisecond pause, and send out that 38K, and then look for the bounce, look for the infrared coming in, and then print out the answer. All right. Right, so obviously we need to keep the debug terminal on our Bobot for this if we're going to do this detector exercise, so that we can actually see the commands being printed to the terminal. And then it says, place an object such as your hand or a sheet of paper about 1 inch in front of the detector, and verify that you get a 0 when you place the object there, and then verify that you get a 1 when you remove the object. Okay. And there's a section on troubleshooting here. We won't go over that, but we'll consult that if we have trouble. All right, your turn. Test the right IR object detector. Okay, so basically we did the left one, so just do the right one, right? So it should just be changing, it looks like pin 8 to pin 2, and then pin 9 to pin 0, and then rerun the program. It should look pretty much the same, except for those 2 pins have changed, and it should act the same. And it should, except for, of course, you'll do the test on the other side. Okay, sine waves synthesized by freakout. The freakout command transmits a rapid sequence of on-off signals that digitally synthesize voltage to create a sine wave pattern. Sine waves sound much more natural than square waves when played by the speaker. Square waves make more buzzing noise. So sine, it's got this nice rounded, what they call a sinusoidal shape to it. Whereas squares, it's got these perfect edges where they rise sharp and drop sharp. The speakers like these rounded edges and not so much these sharp edges. The freakout signal contains 2 sine waves components with 2 different frequencies. One component's frequency is freq 1, and the second is the frequency 65,000 minus freq 1. When the freakout command is used to play audible tones, the signal's second frequency is well above 20,000 kilohertz, which is typically the highest pitch that a human can hear. All right, so example 1, freakout on pin 4 for 2 seconds at 3 kilohertz, plays a 3 kilohertz sine wave tone on the speaker because freak 1 is 3000. The signal contains a second component with a frequency of 65,000 minus 3,000, which is 62,000. But the human ear cannot detect it because it's over, 20,000. Right, you could play the same tone with freak out and then mix them together. Although, all right, so I'm sorry, not mix them together, but you do this freak out command on the same pin for 2 seconds, and then you do 65,000 minus the 3,000. I'll give you the same tone apparently. Although freak 1 is now well outside the human ear's range, the second signal is 3K, so you get the same tone out of your piezo speaker. Okay, and that's because 65,000 minus this 62,000 is 3,000. All right, example 2, on port 8 for 1 millisecond, do a 38,500, makes the infrared LED's brightness vary at a rate of 38K so that the IR receiver can detect it. The signal it creates also contains a second sine wave with 65,000 minus 38,000, or 27,000 hertz, but that signal has no effect on the IR receiver. So interesting little tidbit there, although it seems like it doesn't really matter to either our ear or to the infrared sensor. Okay, activity 2, field testing our object detection and infrared interference. All right, in this activity, you will build the test indicator LEDs that will tell you if an object is detected without the help of a debug terminal. This is handy if you're not near a PC or laptop. All right, we might skip this one. Basically, all we do is we add LEDs yet again onto the top, and you would go ahead and turn those LEDs on when an IR is in one state or the other. So you could either do it when you're detecting it, have it on, or when it's not detected, have it on. But whichever way you would choose to indicate that there's a change in state in that detector. So you would put those on, and you could use that to move. You could move your robot around the room or near whatever your course they're saying, if you were doing some type of course, and you could see if there is infrared in that area, and if there was, then you would know that you'd need to change something on your robot because it's not going to work because you get infrared interference. So that's the code for that there. We're not going to go through it. Okay. All right, infrared detection range adjustments. You may have noticed that brighter car headlights or a brighter flashlight can be used to see objects that are further away when it's dark. By making the Bobot's infrared LED's headlights brighter, you can also increase its detection range. By resisting electric current, by resisting the current less, a smaller resistor allows more current to flow through the LED. More current through the LED is what causes it to glow more brightly. In this activity, you will examine the effects of different resistance values with both red and infrared LEDs. So yeah, the idea here is we get a few different values of LEDs. They got a 470 ohm, or yellow, violet, brown, a 220 ohm, red, red, brown. We got the 2K ohm, red, black, red, and the 4.7, which is the yellow, violet, red. And they're going to swap in all those different values of resistors, and you should see on just a regular old red LED, you should see a change in visible light. In an infrared LED, you should be able to move your object further and further from the infrared receiver, and see how far away it is. It can maximally see, or how far away it can see objects for each value. So the idea is with the higher resistance, you get less current, so your headlight would be dimmer. So this maximum distance should be less. So your maximum distance should be greatest with only the 220 because it's less resistance, so you get more current through to the LED, the infrared LED, and that would cause it to be brighter, although we can't see it. And then you would measure the distance, with a ruler, that you can see the detector showing reflection by moving an object further and further away from the Bobot. So then you would write those distances down, and you should see it, a good distance distribution in here between different resistance values. Okay, activity 4, object detection and avoidance. All right, so this is obviously the most fun one, the most interesting one, although the fact that you can use different distances is interesting as well. An interesting thing about the IR detectors is that their outputs are just like the whiskers. When no object is detected, the output is high, and when the object is detected, the output is low. In this activity, roaming with whiskers from page 178 is modified so that it works with IR detectors. Okay, converting the whiskers program to the IR object detection avoidance. All right, so this next example program started with roaming with whiskers. Aside from adjusting the name and description, 2-bit variables were added to store the states of the IR detectors. Okay, so there's IR detect left, IR detect right as 1-bit variables, so it adds those two. And then it adds these routines to read the infrared object detectors. So we have our freak out command to pin 8 for milliseconds at 38K, and then the input from pin 9, and we put that value into the IR detect left variable. And similarly, the freak out to pin 2 of 38K, and then the read in of 0 for the right side. I should have said pin 0. So the if then else statements were modified so that they look like variables that store the IR object detections instead of the whisker inputs. Right, so before we had something like in 0 and in 9 up here. Now we have IR detect left and IR detect right. And then this should look the exact same. So we have our backup turn left if they're both detecting an object. And then we have IR detect left alone. It does a backup and turn right. That should be the same. IR detect right would back up and turn left. That should be the same. Otherwise, we go forward. So basically, it's the same program as before. We just should be adding these freak out commands and then a quick pull of the input. We can't use the whisker style detection where we used IN0 and IN9 all over the place. We have to do IN0 and IN9 right after the freak out command so we can capture the reflection in the variables left and right. And then we can reuse the variables over here. But if you were to just do the in 0 and in 9, we could very easily miss that reflection because it would take us longer to process it than the light would take to reflect off of an object. Okay, so here's the whole program roaming with IR. Okay, so it's basically the same thing. We have our two new variables up here, detect left and detect right, and then the pulse count variable from the old program. Our freak out to the speaker, which signals the start of the program. And then our big main loop here, the do loop. And yep, right at the front we do our 38,000 output to pin 8, and then we immediately read the reflection from pin 9 so that we don't miss it. Then we do the output of 38K on the other one, would be the right side LED, and then we read in looking for the reflection right away and store that value into right so that we don't miss it. And then later on we can use those values down here, and so that's what we just went over last time. And then these are the exact same. Our forward, left, right, and backup subroutines have not changed at all. Okay, so I think if we get that going, that would be a pretty good start to our first week with infrared. If we get it working and people are having fun and there's plenty of time, we can move on to activity 5. But I will wait for the following week to do a video on activity 5. All right, thanks.